Chapter 7, question 3 is asking you to calculate something called the molar mass for a few different compounds. So let's get a grip on what the molar mass is. The molar mass is the mass of 1 mole of something. Remember that a mole is 1 mole is 6.022 times 10 to the 23rd of something. So it's a group of stuff. 6.022 times 10 to the 23rd things altogether is a mole. That's the name for that group. When we mentioned that, though, in question 1, it might seem weird that they would choose this number. I mean, okay, I get it that we're galactically large. Every time you exhale, you breathe out more atoms than there are stars in our galaxy. So in chemistry, we have to make these groups to make galactic numbers of atoms more intuitive. So that maybe makes sense, but why specifically 6.022 times 10 to the 23rd? Why not just like a round number that's big, but like simple? Okay, and so the reason for that has to do with how we're going to answer these problems. Now you might remember that in previous chapters, we talked about each box on the periodic table having 3 things. It has the symbol in the middle, it has a number on the top, and then it has a number on the bottom. We mentioned how the top number was the atomic number, it's the number of protons. But then we mentioned how the number at the bottom is the mass number. That was the number of protons and neutrons. So the mass of an atom, an individual atom, is 12. But what are the units, or for carbon in this case? It's whatever the number is at the bottom of each box for each element. But what are the units? It's 12, what, 12 pounds? 1 atom? No. The mass of protons and neutrons are so small that it doesn't make sense to measure them in the same sort of units that we have for macroscopic stuff. So instead, they invented a new unit called the atomic mass unit, AMU, and by definition, 1 atomic mass unit is the mass of a proton. So after reasoning through that, we had this beautiful periodic table with a lot of information on it. And underneath each symbol on the periodic table was the atomic mass that told us how many protons and how many neutrons we have. So those numbers are already on the periodic table. The periodic table has a lot of information, and we don't want to make it more crowded and more confusing looking by just putting too much on there. So when people came to start to think about macroscopic stuff, what they said was, okay, we already have this bottom number for the mass on the periodic table. And okay, it's measured in AMU. But what if I took that same number and instead measured out grams? So instead of 12 AMU, I would have 12 grams of this element, carbon. And then they counted up all the atoms that are in that, and it turns out that there were 6.022 times 10 to the 23rd atoms in that. And then they did the same thing for other elements. And they saw, for example, that let's say for oxygen, they measured out 16 grams of oxygen, and they found that that also was 6.022 times 10 to the 23rd atoms of oxygen. So, in other words, the weird number for a mole came from taking the grams for each number at the bottom of the periodic table and finding out how many atoms there were in that. And since 6.022 times 10 to the 23rd atoms is a mole, we can write that many grams equals 1 mole. So you can see that 1 mole of any element will weigh the number of grams at the bottom of each box on the periodic table. So this question is asking you for just that. It's asking you for the molar mass, the mass of 1 mole. So if it were just an element, for example, if we just wanted what's the molar mass of, say, boron? What's the molar mass of that? Well, you'd say, oh, 1 mole of boron would weigh, whatever the number is at the bottom, so here, 10.81, would weigh 10.81 grams of boron. And that would be the molar mass of boron, the mass, number of grams, of 1 mole. Now what they're giving us, though, here is not just one element. They're giving us a whole bunch of stuff. So we'll want to use a method of sort of bookkeeping, along with this principle that we just found, to find the molar mass of these huge compounds. So let's start with cream of tartar, KC4H5O6. The first thing you want to do is to list the different elements you have. Now we want to find out the mass of 1 mole. So we're going to say, okay, we have 1 mole of KC4H5O6. That's the molar mass, the mass of 1 mole. So we know that, and we just want to know how many grams of KC4H5O6 there are in that. So the first thing you want to do to organize your thoughts is to write each of the elements that you have. So we have potassium, we have carbon, we have hydrogen, and we have oxygen. We're going to think about these individually, and then we're going to add them all together. So first, how many potassiums do we have? There's no subscript, so that means that we have 1 potassium. Then what's the mass of each potassium? We'd go to the box on the periodic table that has potassium, sort of on the right side, and we see that the mass there is around 39. Now, most of the time, you can just round these numbers. I realize that they have those like crazy sort of decimals, but you can round them unless they're really close to 0.5. So if they're between like 0.4 and 0.6, like chlorine is at the right side, you can see how it's 0.45, then I wouldn't round them. But if they're below 0.5 or 0.4 or above 0.6 in the decimal, then I would say round them. So we have 1 potassium. We can round that to each mole of potassium weighing 39 grams. So from potassium, we'll be getting 1 times 39 is 39 grams. Okay, for carbon, we have 4 carbons. Each mole of carbon weighs 12 grams. We can see that on the box at the top right of the periodic table. So that means the carbons all together in this molecule will be adding 4 times 12, that's 48 grams. Okay, now hydrogen. We have 5 hydrogens in this molecule. So 5 hydrogens, and each hydrogen, hydrogen's in the top right, each mole of hydrogen weighs 1 gram. So altogether, the hydrogens in this molecule will contribute 5 grams. Then we have 6 oxygens. So 6 oxygens. 1 mole of oxygen weighs around 16 grams. So altogether, that is 96 grams coming from oxygen. So the number of grams in 1 mole of this whole compound will be the sum of all the grams individually. So that'd be 39 plus 48 plus 5 plus 96. That's 188 grams. So there would be 188 grams of KC4H5O6 in 1 mole of this compound. So this whole thing is the molar mass of this compound, cream of tartar. And notice that it's a conversion factor. So later we'll be able to use this to convert from moles to grams. Okay, next. So the next one is rust, Fe2O3. So we're going to go through the same procedure. First, we'll list the elements. So Fe and O. Every time you have a new capital letter, you have a new element. And then we're going to think about them just like we did before. We have 2 irons. And again, the assumption here is that we want to know how many grams of Fe2O3 there are in 1 mole of Fe2O3. That's the molar mass. Okay, so we have two irons, 2 moles of iron and 1 mole of this compound. And each mole of iron, we can see on the periodic table, weighs around 56 grams. So altogether, that would be 112 grams coming from the iron. Then, in 1 mole of this compound, we'd have 3 moles of oxygen. And we can see from the periodic table that each mole of oxygen would weigh 16 grams. So altogether, that's 16 times 3, that's 48 grams coming from oxygen. So we'd have 112 grams coming from the iron, 48 grams coming from the oxygen. Altogether, add those up, and you would have 160 grams in 1 mole of iron. And so that is the molar mass of iron. It's how much 6.022 times 10 to the 23rd atoms of rust would weigh. I realize I just said iron, but this is rust, Fe2O3. Okay, so that's the molar mass there. So we'll follow that same procedure for these next ones. So first, Paxil, the antidepressant. So we want to know if we have 1 mole of C19H20FNO3, how many grams of that would we have? How many grams of C19H20FNO3 would we have? So the first thing we'll do is to list each of the elements we have. Every time you have a new capital letter, you have a new element. So we have carbon, we have hydrogen, we have fluorine, we have nitrogen, and we have oxygen. All right, now, how many, if we had 1 mole of this compound, how many moles of carbon would we have? 19. And we can see from the periodic table that each mole of carbon would weigh 12 grams. So each mole would weigh 12 grams. So altogether, that would be 19 times 12. So that's 228 grams coming from carbon. Okay, how about hydrogen? Well, if we had 1 mole of this whole compound, we would have 20 moles of hydrogen, because in every one of the compound you have 20 hydrogens. So each hydrogen, we can see from the periodic table, weighs 1 gram. So altogether, the hydrogens would weigh 20 times 1 is 20 grams coming from the hydrogens. Okay, fluorine. If we have 1 mole of this compound, we would have 1 mole of fluorine, because nothing is written at the bottom right of fluorine. So we just have 1 mole of fluorine. We can see from the periodic table that 1 mole of fluorine weighs around 19 grams. Oops, 19 grams. So altogether, 1 mole times 19 grams per mole would be 19 grams coming from fluorine. Next, in 1 mole of this compound, we would have 1 mole of nitrogen, because there's no number written at the bottom right of the nitrogen there. So that means that we only have 1. We can see from the periodic table that 1 mole of nitrogen weighs 14 grams. So altogether, we would have 14 grams coming from the nitrogen. All right, next, if we had 1 mole of this compound, so we would have 3 moles of oxygen, because in every one compound, you have 3 oxygens. So 3 moles of oxygen, and we can see from the periodic table that 1 mole of oxygen weighs 16 grams. If 1 mole weighs 16 grams, 3 moles will weigh 48 grams. 3 times 16 is 48. Okay, so those are the masses coming from each element. Now we want to add them all up. So 228 plus 20 plus 19 plus 14 plus 48. That would be 329 grams. So 1 mole of Paxil would weigh 329 grams. So if you ever weigh out Paxil and You have 329 grams of it. You know exactly the number of atoms that are there. 6.022 times 10 to the 23rd, or 1 mole. Okay. Now, let's do this antiperspirant, aluminum sulfate, and a lot of deodorants. So first thing you want to do is to list each element. Oh, and we want to find out how many grams, and if you had 1 mole of this compound, 1 mole of Al2SO4 3, how many grams of the compound would you have? Grams of Al2SO4 3. That's what we want to find out. That's the molar mass. So the first thing we'll do is to list each element. So we have aluminum, we have sulfur, we have oxygen. Now, in 1 mole of this compound, we would have 2 moles of aluminum, because the subscript right next to aluminum is 2. If we go to the periodic table, we can look for aluminum, and we'll see that 1 mole of aluminum weighs 27 grams. So if we have 2 moles of aluminum, that would be 2 times 27, or 54 grams coming from aluminum. All right, if we had 1 mole of this compound, now I know at the bottom right of sulfur it only has a 1, but this whole thing is in parentheses, and you have to distribute whatever's in parentheses to the subscripts. You have to distribute the number at the bottom right outside of the parentheses to whatever's the subscript at the bottom right inside the parentheses for each element. So here we're going to multiply the 3 by the implied 1 at the bottom right of sulfur. So in 1 mole of this whole thing, we would have 3 sulfurs. So it's 3 times 1 sulfur. So 3 sulfurs. If we go to the periodic table, we can see that 1 mole of sulfur weighs 32 grams. So altogether, if 1 mole weighs 32 grams and you have 3 moles, you would have 96 moles, and you would have 96 grams coming from the sulfur in this compound. All right, now the oxygen. Inside parentheses, we have 4 oxygens, but we have a 3 outside, so you have 3 of everything inside the parentheses. So you multiply 3 times 4, and you have 12 oxygens. So the number at the bottom right outside of the parentheses gets distributed to both of the elements inside. So 3 times 4, that's 12. And then if we look at the periodic table, oxygen, so we have 12 moles of oxygen. Each mole weighs around 16 grams. So 16 grams. So 12 times 16, that is 192 grams coming from the oxygen in this compound. Okay, so those are the masses coming from each element. The whole compound will be all of those added together, so 54 plus 96 plus 192, that's 342. So there would be 342 grams in 1 mole of this compound. And that is the molar mass. It tells you how many grams, what the mass is, in 1 mole. Okay. Now, let's do this last one, which is magnesium hydroxide. That's an antacid. So if you ever have heartburn, or you know somebody who has heartburn, they might take this magnesium hydroxide. I think Prilosec is the drug that's used now. So it's the purple pill. So we want to know, if we had 1 mole of this, 1 mole of magnesium hydroxide, how many grams of magnesium hydroxide would that be? And to figure this out, we're going to list each of the elements. So we have magnesium, we have oxygen, we have hydrogen. Now we'll see how many of each that we have, and we'll multiply it by the molar mass of each element. So if we have 1 mole of magnesium, or 1 mole of the whole compound, we would have 1 mole of magnesium, because that's the subscript at the bottom right of magnesium. We know from the periodic table on the right side that 1 mole of magnesium weighs around 24 grams. So if 1 mole weighs 24 grams, and we only have 1 mole in this compound, 24 grams will be coming from the magnesium. Okay, what if if we have 1 mole of this compound, how many moles of oxygen would we have? Well, if we look at the bottom right of oxygen, there's just an implied 1 there. No number is written, and when no number is written, there's an implied 1. But it's inside parentheses, and whenever an element is inside parentheses, we have to multiply its subscript by the subscript outside of the parentheses. So 2 times 1 is 2 moles. For each mole of oxygen, if you look in the periodic table, 1 mole would weigh 16 grams. Because we have 2 moles, there will be a total of 16 times 2, or 32 grams, coming from the oxygen. All right, how about hydrogen? In 1 mole of this compound, we would have, inside parentheses, there's an implied 1 at the bottom right of the hydrogen, but the number outside of the parentheses at the bottom right needs to be distributed to each number inside. So it's 2 times 1, or 2 moles of hydrogen in 1 mole of this compound. If we look at the periodic table, we can see that each mole of hydrogen will weigh 1 gram. So, since we have 2 moles, there will be a total of 2 grams coming from the hydrogen. All right, so those are the masses coming from each of these elements. To find the mass in the molecule overall, we'll add them, so 24 plus 32 plus 2, and that is 58. So in 1 mole of this whole compound, there would be 58 grams. So that would be the molar mass. And think about how powerful this procedure is. We can easily weigh mass. We often weigh our own mass. We walk onto a scale. We can easily put a compound onto a scale and weigh the mass. And what this allows us to do, finding the molar masses, is to figure out the exact number of atoms that we have in that mass. So that's how you find the molar masses of these different compounds using the periodic table. And we'll see that each of these molar masses is a conversion factor that we can use to get a lot of information about how reactions are happening in future exercises.